Hello. Today we will talk about pricing of a European call option. So yesterday we saw the concept of risk neutral evaluation. So we are going to use the same principle. So we'll first compute the expected value of the payoff from the option at capital T, and then we will discount it back to the current time point. Okay. So what do we know about European call option? We know that payoff at time capital T is going to be maximum of 0 comma st minus k, correct? The option will be exercised only if st is greater than k. So if st minus k is positive, then we get this gain. If it's negative, then the option won't be exercised and my payoff will be 0. Okay. So as per risk neutral evaluation, my C would be e raised to minus rt, this is the discounting factor, and then expectation under risk neutral measure of this variable. So that is maximum of 0 comma st minus k. Okay, this is what we have to compute. Now how to find this expectation? Now maximum of 0 comma st minus k can also be written as 0 if st is less than k and st minus k if st is greater than k. The same thing I am representing in a different manner. So this is nothing but st minus k into indicator of this set st greater than k, correct? So when st is less than k, you can include equality anywhere, it doesn't matter, it's a continuous variable. Okay, so when st is greater than k, this indicator would be 0 and hence the entire thing would be 0. Okay, so now we have to find expectation of this random variable under risk neutral measure. So under risk neutral measure here would mean that we will use the normal distribution obtained via Black-Scholes model and we will use R in place of mu. Okay, because that is what we do under risk neutral setup. So we have to compute expectation of st minus k into indicator of st greater than k. Okay, so how to compute this expectation? We can use linearity, so this would become expectation of st into indicator of st greater than k minus, now k is constant so it can come outside the expectation, so k times expectation of indicator of st greater than k. Of course all these expectations are with respect to risk neutral measure. To denote that I am writing p here. Okay, so p is a risk neutral measure. So p is a risk neutral probability measure. Okay, so what is this? Now first part let me right now keep as it is. So expectation of st indicator of st greater than k minus k into this expectation of an indicator function is nothing but probability of the set whose indicator we have, right? This you have learned in probability theory. Other way to think of this is indicator is a Bernoulli variable 0 1. So expectation is probability of success, that is probability of st greater than k. Okay, so this could also be written as probability of st minus k greater than or equal to 0. So let us now try to compute this. We are going to need this later, so let me name this equation 1. So probability of st greater than k is same as probability of ln st greater than ln sk. Am I right? This is because we have log as a monotone function. Okay, so if st is greater than k, ln st is greater than ln k and vice versa. Okay. And we know something about, so why I am bringing in ln st is because we know something about distribution of ln st. and that's normal, so it's easy to handle. Log normal distribution is slightly difficult to handle. So this would be 1 minus probability of ln st less than or equal to ln sk. Okay, and what we know is ln st follows normal distribution with mean ln s naught plus mu minus sigma square by 2 times t comma sigma square t. We have derived this earlier. Okay, of course this is conditional distribution, ln st given s naught, but now anyway we are assuming that s naught is known, the present or at time 0 the price is known, so we can use this distribution. And because we have to use risk neutral measure, this mu would be replaced by r. Okay, so my probability of st greater than k becomes 1 minus probability of, now let me use properties of normal distribution. So I'll write ln st minus, I will subtract the mean, so mean is ln s naught minus r minus sigma square by 2 because of risk neutral thing, t. Okay, and then we have to divide by the standard deviation. Okay, so this is sigma square by 2. Okay, so sigma root t. Okay, so this is less than or equal to ln k minus same thing here divided by sigma root t. Okay, so this is 1 minus, and now this becomes my standard normal variate, correct? Because I have a normal variate minus its mean divided by standard deviation. So this is CDF of standard normal variate at this point. So what is this point? ln of k minus ln of s naught. Okay, this has to be plus here. Okay, outside the bracket it would be minus. So ln s naught minus r minus sigma square by 2 times t divided by sigma root t. Okay, so this is 1 minus CDF at this point, and we can use symmetry of normal distribution. So this will be, so 1 minus CDF at x is CDF at minus x. Okay, so this is phi at minus ln k plus ln s naught plus r minus sigma square by 2 times t divided by sigma root t. We can slightly simplify this, so this would be written as ln of s naught upon k. Okay, ln s naught minus ln k I can write as this plus r minus sigma square by 2 times t divided by sigma root t. Okay, so this quantity we are going to call as d2. Why 2? Because it's in the second term of the original expression, and this will become phi of d2. Okay, so we have simplified the second term from equation 1. Okay, now we have to worry about first term. So let us worry about the first term. The first term is expectation of st into indicator of st greater than k. So random variable is involved in both these functions, st here as well as here. Okay, so let us try to write this in the form of expectation that we know. So again first let me bring in ln st. Okay, because that would make things simpler. So this can be written as e raised to ln st, indicator of, this I can again write as ln st greater than ln k. Okay, so let ln st be written as y. Okay, then this expectation becomes e raised to y, indicator of y greater than ln k. Okay, now let us try to use the PDF of normal distribution and actually write down the integration. Okay, see, I want expectation of this with indicator. So you know from probability theory, if I take integral over only that set, okay, so e raised to y into PDF of y dy, then that would serve the purpose. Okay, multiplying by indicator is nothing but taking integral over that set. Okay, so this becomes integral y greater than ln k e raised to y, and now PDF of normal. So 1 upon sigma root t, of course root 2 pi, e raised to minus half sigma square t, and then y minus whatever is its mean whole square into dy. Okay, now where we know the mean, so mean is ln of s naught plus r minus sigma square by 2 times t. Okay, so this would be 1 upon sigma under root 2 pi t. Now we have to expand the whole square, and the last term would be free from y, so it's a constant, so it can come outside. So I will have e raised to minus, okay, so inside the bracket this would be plus m square and with minus sign, so this would become minus m square upon 2 sigma square t. Inside the integral I still have e raised to y and then e raised to minus 1 by 2 sigma square t y square minus 2my. Is it okay? dy. Everyone with me so far? Okay, the expressions seem long, but we are not doing anything very extraordinary. Okay, we are just writing down PDF of normal distribution and doing some rearrangements. Okay, so this becomes 1 upon sigma root 2 pi t. This again I'll keep as it is, m square upon 2 sigma square t. Okay, now integral y greater than ln k is also fine. E raised to minus 1 by 2 sigma square t, and I will have y square minus 2my, and if I want to bring this y inside, then I will have to have, I have a minus sign here, so it will become minus y, and because I have a denominator, so 2 sigma square t, correct, into dy. Okay so far? So this becomes 1 upon sigma root 2 pi t. So you know we are trying to do completion of square and something like that. So y greater than ln k e raised to, okay, so this is y square minus 2m plus 2 sigma square t into y and then dy. Okay, so I can see that these are, I mean the terms inside this are first two terms from y minus m plus sigma square t whole square. Okay, let me write what I am saying. Okay, so let us try to complete square here. I am sure you must have done something like this when you were dealing with things like MGF of normal distribution, etc. So let me introduce a new variable u as y minus m plus sigma square t divided by sigma root t. Okay, why this? Because you know this looks like a term coming from m plus sigma square t. Okay, of course when you do this you have to adjust. Du would become dy upon sigma root t. Okay, du would become dy upon sigma root t. Okay, and the range also changes, correct? Y greater than ln k is equivalent to u greater than ln k minus m plus sigma square t divided by sigma root t. Okay, so let us put all those things. So now I need sigma root t with dy to make it du. So this sigma root t would go there, root 2 pi can stay here for the time being. So I'll be left with 1 upon root 2 pi. This term I'll keep as it is. So e raised to minus m square upon 2 sigma square t. Then integral u greater than ln k minus m plus sigma square t divided by sigma root t. And now here I'll have e raised to, okay, so now we will be left with just minus half u square, correct? Because u square would be, because I'm trying to complete the square, u square would be y square minus 2m plus 2 sigma square t into y plus this m plus sigma square t whole square. So we have to adjust for that m plus sigma square t thing also. So I'll have e raised to m plus sigma square t whole square divided by sigma square t 2. This comes by completing square. So we have to compensate for completion of square into du because we have taken sigma root t inside. Okay. So now we can again take this constant term outside. So I am left with 1 upon root 2 pi e raised to minus m square, and then we have this m plus sigma square t whole square. So that becomes m square plus sigma 4 t square plus 2m sigma square t, correct, divided by 2 sigma square t. And here I have u greater than ln k minus m plus sigma square t divided by sigma root t e raised to minus half u square du. Okay, so now let me take this 1 by root 2 pi also inside the integral. So I have e raised to, m square gets cancelled. From these terms I can cancel sigma square, I can cancel 1 t. So I'll be left with what I'll be left with is one single t with sigma square plus 2m divided by 2, correct? E raised to 2m plus sigma square t divided by 2, and u greater than ln k, this remains as it is. And now I have 1 upon root 2 pi e raised to minus half u square du. Does this term inside the integral sign look familiar? Okay, so this is your PDF of standard normal random variable. So we are basically integrating PDF of standard normal variable over some range. So that is nothing but something related to CDF. Am I right? And because we are integrating over range u greater than something, it would be 1 minus CDF. So I'll have 1 minus CDF of standard normal at ln k minus m plus sigma square t divided by sigma root t. Okay. Again we can simplify it. So this is e raised to 2m plus sigma square t by 2, and this again can be written as phi at minus of the inside thing. So phi of minus ln k plus m plus sigma square t divided by sigma root t Okay, so we have to substitute m also. So far we have not substituted for m, so let me try that now. So I have minus ln k plus m plus sigma square t divided by sigma root t. So this is nothing but minus ln k plus, let me substitute for m. M is ln s naught plus r minus sigma square by 2 times t, plus we have sigma square t divided by sigma root t. So this is ln of s naught by k plus, now I have minus sigma square by 2 and plus sigma square. So I'll be left with r plus sigma square by 2 times t, correct? R plus sigma square by 2 times t divided by sigma root t. Okay, and let me call this complicated term as d1, just like we had named the earlier term as d2. So this becomes the expectation that we are interested in. So we have to substitute value of m in this first term also. Okay, so let us try to do that now. So e raised to 2m plus sigma square t by 2. So here also we have to substitute m. So this would be e raised to 2 times m would be 2 times ln s naught plus 2 times r minus sigma square by 2 t plus sigma square t whole thing divided by 2. Okay, so this is e raised to 2 ln s naught plus 2r minus sigma square t plus sigma square t divided by 2. So this is e raised to ln s naught plus r, correct? And e raised to ln s naught, sorry, I have to take this t also, okay, I can't forget that. So rt, ln s naught plus rt. And what is e raised to ln s naught? So I have e raised to ln s naught into e raised to rt, correct? So this is s naught e raised to rt. Is it okay? E raised, I mean the simplification. Okay, so now let us substitute all these things. So expected payoff we had written as expectation of ST, indicator of ST greater than K, minus K times probability of ST greater than K. Okay, that was my expected payoff. So let us try to substitute the values. So this expectation of ST into indicator ST greater than K, we have computed this term just now. Okay, so this is S naught e raised to RT into something. So what is that thing? Let us check. So into this CDF at D1. Okay, phi at D1 minus K times, and probability of ST greater than K also we have computed. So probability of ST greater than K is phi of D2. Okay, so phi of D2. But finally what we want is call price. So call price is discounted version of this expected payoff. So e raised to minus RT times S naught e raised to RT phi D1 minus K phi D2. So this becomes S naught phi D1 minus K e raised to minus RT phi D2. Okay, my final formula for call option price is S naught phi D1 minus K raised to minus RT phi D2, where D1 and D2 have been defined earlier. Is it okay? So this is how we get price of a European call option we can see that this price is a function of many things. So D1 and D2 themselves involve many terms. So K, R, sigma, etc. Okay, so the price is a function of everything: current stock price, volatility, the time duration, strike price, etc. And how they affect means what happens if strike price increases and everything else is kept constant, etc. We have to check later. Okay. I have a small homework for you. So two homeworks actually. First homework is you have to derive relationship between D1 and D2. You can see that D2 is D1 minus sigma root T. Verify that. And second homework is derive price for the put option. Okay. What is the price for European put option? You have to go in exactly similar manner. So first see what is the payoff at time capital T, then compute expected payoff and then discount it back. And I'm going to give you a final expression just so you can verify whether you are doing it correctly. So it will be K e raised to minus RT phi minus D2 minus S0 phi minus D1. Okay, D1 D2 are exactly same as what we used in call option price. Okay, so this should be your final answer. So try to verify what happens. Okay. Let me stop here. Thank you.